we're going to focus on a subset of one-dimensional motion in which you have constant acceleration. This is our acceleration graph right here, that we have some non-zero value for acceleration that doesn't change. So maybe this would be like our acceleration graph. Okay, if that's the case, then that means that we have a velocity that's changing. Okay, in this case, it's getting more positive. Okay, or if we started at negative, it became 0 and then more positive, or it got less negative. So it might look something like this for velocity. Okay, and so to go with that, in a position graph, that might look something like, it would be quadratic. Okay, so this would be position, velocity, and acceleration. Okay, and so just a couple of things that we know so far. We know that we can go from position to velocity by finding the slope. So if we find the slope at any point on here, that gives us velocity. And really, to go from here to here, that'd be the slope of the tangent line. Okay, and so that v is equal to dx dt. And that the slope of this line is equal to the acceleration. So a equal to dv dt. Okay, and we can go backwards, because if we find the area of this, okay, that's going to give us displacement. So delta x equals v times t. Okay, and then we can actually do the same thing right here. If we find the area under here, we can get the change in velocity. Change in velocity is equal to a times t. Okay, and so we know these relationships, and this particular set of circumstances where the acceleration is constant is important because it's something that comes up a lot. And so it's actually really tricky to have a scenario where acceleration is actually constant, but there's a lot of times when it's relatively constant, and it's constant enough where we can assume that it's constant. And in those situations, we have some really powerful tools for making predictions about the way things behave. Okay, and that's what we're going to be exploring for the rest of this chapter. Okay, and we're going to start that exploration by looking at the velocity graph. Okay, and so let's do that. Okay, so here we have a velocity graph. You can see that this velocity graph is linear, which is an indicator that we're experiencing constant acceleration. If you remember back, in maybe the first or second week, we came up with an equation that looked like this, that represented the position of an object when it had a constant velocity. Okay, so this equation represents position of an object that's moving at a constant speed. Okay, this equation breaks apart though if the velocity is changing and no longer is valuable in circumstances like this where we have a changing velocity. But we can use this as an analogy to write a similar equation for velocity. Okay, and so we're going to ignore this one right now and create a new one for velocity. And so if we want to write an equation that shows what the velocity is depending on how much time has passed, we're gonna basically write a general equation for this line. Okay, so v equals, it's linear, so mx plus b, so something times t plus something. Okay, and so what if we remember back, what does the slope of the velocity graph represent? Like, what quantity do we find when we find the slope of our velocity graph? Well, we have acceleration, so instead of m here, we're going to put a for acceleration, because the slope of our velocity graph is acceleration. Okay, and then for the starting point, we'll call this starting point v naught, or v initial. Okay, starting velocity. Okay, and so now we have an equation, a linear equation for velocity. And so this equation here is only true when acceleration is constant. If you have a constant acceleration, then we can have this relationship that basically we could use the amount of time and starting velocity and acceleration to figure out how fast something's moving over time. And really we can use this equation to solve for any of these pieces. And so here we have our first of what we're going to have several of, called constant acceleration equations or kinematics equations. Okay, so that will be our first one. And we can actually rework this too. So if we solve this equation for A, we find that V minus V naught equals A times T. If we divide the T over, we get A is equal to V minus V naught over T. And this is something we know, right? If acceleration is truly the slope of velocity, then this is basically saying acceleration, and this is kind of like the slope equation, right? Change in V over the change in time. Okay, and so these are just two versions of the same equation. This is an equation that we have already been using without realizing it. So an interesting thing happens here. When we do have constant acceleration, if we have some time interval t, okay, which we'll have right here, if we were to take the velocity at the end and the velocity at the beginning and divide them by 2, so find the average of the two, then that's actually going to be equal to our average velocity. Okay, and this again is only true when acceleration is constant. Okay, so in this circumstance with constant acceleration, the average of this value right here and this value right here is going to be something right in the middle, which would be equivalent to the average velocity in this circumstance. And it might help you to see it on a position graph. You might see a little bit why. So if I have some quadratic function, okay, and this is only true of quadratics, if I find the slope between 2 points, okay, the slope of that line is going to be the same as the slope of the tangent line that occurs halfway between those points. Okay, and this is basically another way of saying this right here. And so this also is actually one of our kinematics equations. We're not really going to use this one that much, but it is one, and we can use it to derive some different, more powerful and more useful equations. Okay, so the next one we're going to come up with is going to be an equation that relates displacement, acceleration, velocity. We're going to start right here with this velocity graph. Okay, and so in our velocity graph, if you remember, when we find the area, we can get displacement. And so I'm going to take this shape, I'm going to break it into two pieces, and we're going to find the area of it. Okay, and so if we find the area of this piece right here, so we're going to say that delta x is going to be equal to the area. So the area of this rectangle right here is going to has a height of v naught and a width of t. So we'll call that v naught times t. And then we have this triangle here. Area of a triangle is going to be 1/2, and this is a height of, it's like a height that from v naught to some amount v, and so it's like the difference between those. So it'd be v naught minus v, and then times the width here of t. So the area of this is 1/2 v naught minus v times t. Okay, so the t again is the width, and the v naught, or I have it backwards, I guess this would be v minus v naught, and this comes from the difference from the lowest part here to the highest part, so our starting velocity to wherever we ended up. Okay, so I've got these backwards. Okay, and so as we're working with this equation, what's going to be helpful is if we can simplify this. And you might notice that we've already have this written somewhere on the screen here with this equation right here. So we see this, we can actually rewrite this equation so it looks like a times t equals v minus v naught. And then we can take this right here and replace it, and replace v minus v naught with it. So we would then have delta x equals v naught t plus 1/2 times at times t. Okay, and then we could simplify this and get delta x equals v naught t plus 1/2 at squared. Okay, and this is an equation that represents the displacement of an object. Okay, you might also see it referenced as position, and instead of doing delta x, you might see x minus starting position. Okay, but we'll use it in this form right here. Okay, before we continue, what happens if you were to take the derivative of this function? If you were to take the derivative of this function, you should end up back right here. Okay, or yeah, right here, except with maybe the v naught in the front. Okay, if you take the derivative with respect to time, this becomes dx dt, or v. Okay, 1 times v naught is v naught, 2 times 1/2 is 1, and we subtract 1, leaving us with at. Okay, and so you can see that these two equations are actually related here through calculus. Okay, so now we have 1, 2, 3 equations.